In this video, we are going to discuss our last type of force for this unit, called the force due to friction. The force due to friction is the resistance to motion. So it's due to the fact that the surface of the object and the surface of the surface is not perfectly flat. So as the molecules that are jagged rub up against each other, there is resistance. Now there are some scenarios where the force due to friction and the motion of the object are in the same direction, but we're going to deal here only with situations where the friction is anti-parallel to the motion of the object. So it's going to oppose the motion of the object. So as the object is trying to move forward in the positive x, the friction will be in the negative x. If the object is trying to move up a wall, the friction from the wall on the object is going to be in the negative y direction. So in the scenarios we're discussing, the friction is always going to be in the opposite direction of the object is actually moving or is trying to move. Now there are two different types of friction, one for when you're at rest and one when you're in motion. So the force due to static friction applies when the object is not yet moving but you are trying to get it to move. The force due to static friction is less than or equal to the coefficient of static friction times the force normal. You already know what the force normal is, so let's talk about the coefficient of static friction. The coefficient of static friction is a unitless number that characterizes how much friction there is between two different types of surfaces. So a flat piece of metal sliding against ice is going to have a very low coefficient of friction, but if you take a very rough piece of sandpaper and try to put it up against another rough piece of sandpaper, that's going to have a very high coefficient of static friction because it's very jagged, so there's going to be more edges that catch on each other, so there is more friction. We have to be careful not to mix up the coefficient of friction and the force due to friction. The coefficient of friction is based upon the two surfaces, but the amount of friction you actually have also depends upon the force normal. So how much the surface is actually pushing up on the object. The more the surface has to push up on the object, the more friction there is. So the force due to friction has units of newtons, the coefficient has no units. Now notice that this is an inequality rather than an equation. We like to do it in equations though. So the force due to friction static increases as more force is applied. So if you have a box sitting on the surface, the more force you apply to the box, the more static friction is going to resist. So if you push with 50 newtons, the static friction is going to push back with 50 newtons. And this is going to continue to happen, so if you push with 60, it'll push back with 60 until you reach the maximum static friction. There's a point where the static friction does not increase anymore, and then you can push with more force than the maximum static friction and actually get the object to move. So the maximum force due to static friction is the minimum force required to just start the object in motion. Once we start the object in motion, we start talking about a different type of friction because we're no longer static, we're kinetic. Now once the object is in motion, we switch from the force due to static friction to the force due to kinetic friction. So the force due to kinetic friction only applies once the object is in motion. The force due to kinetic friction is equal to the coefficient of kinetic friction times the force normal. And the coefficient of kinetic friction is different than the coefficient of static friction. Typically it is a lower value. It actually requires less force to keep something in motion than it does to actually start it in motion. So this is why if you're pushing a heavy object and you're pushing and pushing and pushing, and then all of a sudden it starts moving and you kind of fall forward, this is because you've now overcome the force due to static friction, which is a higher value than the force due to kinetic friction. So now that you've dropped down into the kinetic friction, you have an overabundance of force to push the object forward. So it's actually easier if you can continue to push forward rather than stopping and starting, stopping and starting, because then you don't have to keep overcoming the force due to static friction, which is a higher value. Coefficients of friction are typically somewhere between 0 and 1, or something like ice might have a coefficient of friction of 0.01. You can have coefficients of friction of greater than 1, but it's a pretty unusual situation. And these are numbers that will I'll typically give you in a problem. Sometimes you'll find tables of them in the textbook for specific substances. However, you do have to realize that you're either at rest or you're in motion. You can't be both at the same time. So that means any application of Newton's second law should only ever have one force due to friction, either static or kinetic, even if you're given both coefficients in the problem. So you need to read the problem and decide if you're at rest and trying to move or whether you're already in motion. That allows you to decide which coefficient to use and therefore which force due to friction to use. You should never be using both in the same Newton's law equation. Alright, so I'm going to use the person to apply a force to the box. So notice that my force applied is equal but opposite to my force due to friction. So the object is not yet moving. And as I apply more force, that force due to friction increases until you hit a point where the force applied is greater than the force due to friction, and you overcome the static friction and we start moving. And if I could show this in slow-mo, you can actually see that the force due to friction drops down a little bit. So if you scroll back a little bit and pause the video, you can actually see that drop down. And up in the corner, it's cut off a little bit, but you can see that the speed is increasing because I have a net force that's in the positive x direction. But now if I let go and stop applying a force, now the net force is in the x direction because the friction is the only force acting and it's opposing the motion. So now the object is decelerating because the force is in the negative x direction. So once you let go, the only force acting on it is the force due to friction, and the object decelerates until it comes to a stop.